So far in our work with the binomial expansion, we've been looking at expanding binomials to a positive integer power. We have the form a plus b to the power of n, where n is a positive integer, and this gave us now a finite number of terms, and we could write that now as nc0. We had a to the power of n, and then b to the power of 0, plus nc1. We had a to the power of n minus 1 multiplied by b to the power of 1, plus nc2. We had a to the power of n minus 2, and then we had b to the power of 2, right up now to the final term when we had ncn. We had a to the power of 0 and b to the power of n. We could write this term now as nc0 and then just a to the power of n, as we know b to the 0 is 1. In the same way we can write the final term now as ncn b to the n, as a to the 0 is 1. So this is one way that we could expand a binomial when we had a positive integer power. There is an alternative, and this leads to something called the binomial theorem. Now, the advantage of the next method is that it holds true when n is not a positive integer. So for any rational index, this will work. And it's adapted slightly when we have a negative or fractional number. So what we're going to do is let a be equal to 1, and we let b be equal to x. So a is equal to 1 and b is equal to x. So what we have is the expansion of 1 plus x to the power of n. If we do this, we get the result 1 plus n multiplied by x plus n multiplied by n minus 1 multiplied by x squared over 2 factorial plus n multiplied by n minus 1 n minus 2, and then we have x cubed over 3 factorial, and we continue this right the way up to the final term. And again, this is for a finite expansion, so we'll have a finite number of terms. When we have an infinite series expansion, this is just adapted very slightly, but we end up now with x to the n. So with this particular method, we could go ahead, for example, and expand 1 plus x to the minus 4, or we could have now 1 plus x to the 1/4 power. So this is an alternative expansion when we have now 1 plus x to the n, and again, for this particular form, n is going to be a positive integer, and that gives us now a finite number of terms, and it's just n plus 1 terms. Okay, there is an alternative on this, and that's going to be 1 plus ax to the n, and I actually prefer this, especially when you're expanding. So we got 1 plus x to the n. We could write this as 1 plus ax to the n, so we're just considering now a coefficient on the x term, and this is going to give us 1 plus n multiplied by ax, and then we'll get plus n, and then we'll have n minus 1. We will have ax, which we square, and then we put this now over 2 factorial plus ... and so on and so forth. So all we're doing now is having ax. And again, sometimes you might see that in a book, sometimes not. So that's one particular way. Now there are advantages and disadvantages of both. So for example, now if I was expanding, let's say I was expanding 3 plus 2x to the power of 4, we know, of course, 4 is a positive integer value. I'd just go ahead and use this particular approach. Yet if I had now 1 minus 2x to the power now of, let's say, 6, I might use the second one. I certainly would use it if I had 1 plus, let's say, 4x to the power of minus 3. Also, I could use this now if I had an unknown power. So if we had, for example, 1 plus 2x to the power of p, I'd go ahead and use the binomial theorem to expand. Now let's just have a look at the two different forms. When we have now nc0, we know that that's going to be equal to 1. If we just consider nc1, what we have is ncr, and we've seen from previous videos that this is n factorial over r factorial, and then we'll have now n minus r factorial. So if we just consider now nc1, if we think about nc1, and I'll just write this down, nc1. Now in terms of having to show this or explain this, this isn't necessary, but I think it's important just to do it anyway. So what we're going to have then is n factorial over 1 factorial multiplied by n minus 1 factorial. And we looked at these factorials before. Now if we consider n factorial is n multiplied by n minus 1 factorial, and that's over now 1 factorial, which of course is just 1, and then we have now n minus 1 factorial. We can see that they're going to cancel, and that's why we can now make the substitution just here. So what we have instead of nc1, we're going to have n just here. Now if we look at nc2, let's write nc2. If we have nc2, this is going to give us n factorial over now the 2 factorial, and then we're going to have now n minus 2 factorial. So if I consider n factorial is n, and then we're going to have multiplied by, and then the next one is going to be n minus 1, and then we'll have n minus 2 factorial. That is n factorial relative to what we've got in the denominator. 2 factorial is just 2, and then we have now n minus 2 factorial. They're going to cancel, and we can see now why we're getting n minus 1 over 2 factorial multiplied by x squared. So this just gives us the coefficient. So as stated, this will be quoted, and it's in this form now when we have a finite series expansion, and then when we have an infinite one, there's a slight alteration here, and we do cover that in a later video. Okay. Now, what are the disadvantages of using this particular method now when we have this form? Well, the answer is that we need 1 in the front of a bracket. So in this particular case, what we'd have to do now is take the 3 out. So we would take the 3 out, raise it to the power of 4, and we'd have 1 plus 2 over 3x to the power of 4. So what we'd essentially have now is 81, and then we would go ahead and expand. And again, you might think that's a bit laborious, but certainly now when n is not a positive integer and it's just some rational power, then this is the approach that we would take. So what we're going to do is look at using this particular method on a binomial expansion, and then look at a question where it would be more advantageous to use that second form. So let's go ahead now and use it, and let's just expand. We'll go for 1 plus qx, and we'll take this now to the power, let's go to the power of 3. So what we're going to do is use the method, and we'll have 1 plus, and I'll just use the 1 plus ax to the power of n method. If we do this, we're going to get 1 plus n multiplied by ax, and then we're going to get plus n multiplied by n minus 1 multiplied now by x squared over 2 factorial. Then we'll get now plus n, we will have n minus 1, we'll have n minus 2, and then we'll have x cubed over 3 factorial. Now 2 factorial is 2, 3 factorial is going to be 6. So in this particular expansion now, what we'd simply have is 1 plus, and then n is going to be 3. So we'd have 3 multiplied by qx. Then we're going to have now 3 multiplied by 3 minus 1, which is going to give me 2. Then we're going to have now our term qx. We're going to square that bracket and divide it now by 2 factorial. 2 factorial is just 2 times 1, so that's going to give me 2. Plus now we're going to have n, which is going to be 3, n minus 1, which is going to be 2, n minus 2, which is going to be 1. We have qx, we cube this bracket, and we divide by 3 factorial. 3 factorial is just 3 times 2 times 1, which is going to give us 6. Or you could just see that it's going to cancel here. So we have 1 plus 3qx. We can see now that the 2's are going to cancel, so we have plus 3. Now this gives us q squared x squared, and that's why I prefer the method of 1 plus ax. Often students forget to square the q. We can see the 3, the 2, the 1 and the 6 are going to cancel, so this will give us now q cubed x cubed. So we can see again we get 4 terms using the expansion in that particular way. Now of course you could have used the NCR method, or you could have used Pascal's triangle to do that. But that's now using the particular method of the binomial theorem. Again, if we had, for example, now let's say we've got 2 plus x to the power, and let's go now to the power of 4. And let's just say we wanted let's go for the first 3 terms. So if we use now the binomial expansion, we would have now our basic expansion, we would have 2, and now we would have this to the power. So let's just write the coefficients out, 1, 4, 6, 4, 1. So that would be using Pascal's triangle. So we'd have now 1, then we'd have now 2 to the power of 4, we'd have x to the power of 0, plus now 4, then we'd have now 2 to the power of 3, and we'd have x to the power of 1, and then we'd have plus 6, and then we'd have now 2 to the power of 2, and then we'd have x squared. So if we did this, this is just going to give us now 2 to the 4th, which is 16, plus now 4 lots of 2 to the power of 3, so that's 4 times 8, which is going to be 32x, and then we get plus 24x squared. So that would be using the method right there. And as you can see, that's a nice straightforward one. Now, what we'd have to do if we wanted to use the 1+ax method is write this now as 2 to the power of 4. Then we would take, as we're taking the 2 out, this would give us 1 plus x over 2 now, and we would raise this to the power of 4. And then we would go ahead and expand. So what we'd have is 2 to the power of 4, which is going to be 16. We would then have now, using the particular form of 1 plus ax to the n, we would have now 1 plus, and then we'd have n multiplied by ax. Now in this particular case, the term a is going to be a half. So we'd have 4 plus 1/2 x. Then we'd have now plus n, which is going to be 4. Then we'd have n minus 1, which is going to be 3. Then we're going to take ax, which is going to be 1/2 x, and we square this. So it's going to be 1/2 x squared. And then we divide now by 2 factorial. Dividing by 2 factorial is the same as multiplying by 1/2. So you can see with this particular approach, it's going to get quite messy. So what we end up with then is the following. We've got 16, and then we're going to have now on here, that's going to be the 1 plus 2x. Now if we consider what we're going to get here, this is going to be 1/4 x squared. So the 4 and the quarter will cancel. We've got now 3 over 2 x squared. So plus 3 over 2, and then we got x squared, and then we have the other terms. So if we multiply through at this stage, what we're going to have then is 16 plus now 32x. 16 times by 3 over 2 is going to give me plus 24x squared, dot, 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 and so on and so forth. And we can see that gives us the same expansion here. So it's quite laborious to use that particular method when we have to take the 2 out and raise it to the 4th power. This one is significantly easier just to write it out when n is a positive integer. But again, if it wasn't, we would use this method. So if this was -1, we would sub in n is equal to -1. So we'd have now -1, we'd have -1 minus 2, we'd have -1 minus 2 minus 3, and so on and so forth. And that would give us our infinite series expansion. What we're now going to do is look at where this would be beneficial, this 1+